Imagine standing in a pitch-black room completely enveloped by darkness. There's absolutely nothing to see, no hint of light, just pure, unadulterated blackness surrounding you. Now, imagine holding a feather in your hand. It's so light, so delicate, you can barely feel its presence. Suddenly, a powerful spotlight turns on, piercing through the darkness. It floods the room with light, banishing the shadows and revealing everything in stark detail. You wouldn't expect the feather to move. It's just a feather after all. And light is weightless, right? It's just energy, pure and simple. But here's the cosmic puzzle. A mind-bending paradox that challenges our understanding of the universe. Light, with no mass, can actually push things. It can exert a force, however small, on physical objects. Unlike a bowling ball or the wind, things we know have force, which have mass and therefore momentum. Light has zero rest mass. It's pure energy in motion, so how can it exert any force? How can something with no mass possibly move something that does? Yet, the universe is filled with evidence that it does. Everywhere we look, light is shaping the cosmos. Every star, including our sun, that sustains life on Earth blasts out torrents of light, a constant stream of photons radiating outwards. Energy that, somehow defying all expectations, can move matter. It can push, pull, and shape the very fabric of reality. If this massless energy can push, if it can exert a force on the world around us, its effects across cosmic timescales could be monumental. It could explain some of the greatest mysteries of the universe. To solve this riddle, to unravel this cosmic paradox, we need to leave behind our everyday world, our intuitive understanding of how things work. We must dive into the quantum realm, the bizarre and counterintuitive world of the very small, where the rules are different, where the familiar laws of physics break down. Here, energy and matter interact in strange and wonderful ways, in ways that defy common sense, challenging our deepest assumptions about the nature of reality. Our journey begins with a single fundamental particle, the smallest unit of light, a tiny messenger that carries the secret, the key to understanding, of light's impossible push, the very thing that makes it possible for light to move matter. Let's go meet the photon and uncover its secrets. Scene transition. What exactly is light? It's a question that has puzzled scientists and philosophers for centuries. Is it a wave, spreading out like ripples in a pond? Or is it a particle, a discrete unit of energy? The answer, surprisingly, is both. Light exhibits a dual nature, behaving as both a wave and a particle, but it's the particle side, the photon, that holds the key to understanding its fundamental nature. Think of light not as a continuous stream but as a shower of tiny discrete packets of energy. These packets are what we call photons. Each individual photon has no rest mass, meaning it doesn't possess mass when it's at rest, but it's always without exception, moving at the speed of light, the ultimate speed limit in the universe. Thanks to Einstein and his groundbreaking theories, we know that energy and mass are fundamentally two sides of the same coin, interchangeable under the right conditions. So, while a photon itself has no mass, its inherent energy, dictated by its frequency, gives it momentum, a push, a force, born from pure energy perpetually in motion. When a photon, traveling at the speed of light, strikes a surface, it transfers a tiny bit of this momentum, delivering a minuscule, almost imperceptible push. The push from one single photon is incredibly minuscule, practically negligible, but when you consider trillions upon trillions of photons, like the constant stream emanating from a distant star, that accumulated force, that combined energy, can add up to a very real and measurable force. This is how light, which seems so ethereal and weightless, can, over vast cosmic timescales, sculpt the very fabric of the cosmos, shaping galaxies and influencing the movement of celestial bodies. Imagine countless photons, each a tiny packet of light energy, relentlessly streaming outwards from a star. The collective push, the combined force from these countless photons, is what we call radiation pressure. It's a subtle but persistent force. Here on Earth, shielded by our atmosphere, it's far too weak to feel directly. We don't notice it in our daily lives. But out in the vast emptiness of space, where there's nothing to block or diminish it, radiation pressure can have dramatic and far-reaching effects. Just look at a comet's beautiful flowing dust tail, a stunning example of this force in action. That tail is being constantly pushed away from the sun, sculpted and shaped by nothing more than the gentle pressure of sunlight. Each individual photon imparts only a tiny nudge to each dust particle, an almost imperceptible push. But when you add up the effect of trillions upon trillions of these photons, the result is a spectacular tail stretching millions of kilometers long, and we can even harness this seemingly weak force for our own purposes, with the development of solar sails. These are essentially giant, incredibly thin and reflective sheets, designed to maximize the surface area exposed to sunlight. They catch the sunlight, intercepting those photons and using their momentum to generate a continuous, gentle thrust for propulsion. The LightSail 2 mission provided definitive proof that this concept is not just theoretical, it's real, and it works. It successfully demonstrated the ability to use sunlight to gradually but measurably raise its orbit around Earth. Given enough time, solar sails could potentially propel spacecraft to incredible speeds, far beyond what's currently achievable with conventional rockets. This opens up the tantalizing possibility of interstellar travel, allowing us to reach distant stars and explore the cosmos like never before. And it's all thanks to the fact that light, even though it's weightless and intangible, carries momentum, a tiny but significant amount of force, and can therefore push the universe around it, shaping celestial objects and enabling new forms of space travel. Scene transition. To understand how something massless can push, picture a machine gun firing ping-pong balls at a heavy medicine ball. One ping-pong ball does nothing but billions per second. The medicine ball starts to move. That's how radiation pressure works. Photons are the ping-pong balls, and objects in space are the medicine ball. The sun bombards every square meter of space with over a quadrillion photons each second. The push from each is tiny, but together they create a real constant force. This effect is strongest on light-reflective objects like mirrors or solar sails. When a photon bounces off a mirror, it transfers twice the momentum, giving the mirror a stronger push. Scientists use this principle for precise measurements in the lab. So, can you weigh light? Not in the traditional sense, light has no rest mass, so it can't be weighed on a scale. But we can measure its effects. Early experiments used delicate torsion balances to detect the tiny push of light on mirrors. Today, lasers and optical tweezers let us move microscopic objects using only the momentum of photons. This technology has revolutionized biology and nanotechnology. We can't weigh light, but we can measure its force with astonishing precision. Light, the massless messenger, carries energy and momentum, pushing dust, propelling spacecraft, and shaping the universe. It's invisible and weightless, but powerful enough to change everything.